Two parallel rails with negligible resistance are 13.5 centimeters apart and are connected by a resistor of resistance R3 is equal to 5 ohms. The circuit also contains two metal rods having resistances of 13.5 ohms and 15 ohms sliding along the rails as in the figure below. The rods are pulled away from the resistor as constant speeds of 4 meters per second and 2 meters per second respectively. A uniform magnetic field of magnitude 0.01 T is applied perpendicular to the plane of the rails. Determine the current in resistor number 3.
Alright, so this is problem number 8. We got a rod on the top, a rod on the bottom. We got one rod moving to the left at 4 meters per second. One rod moving to the right at 2 meters per second. And it says that they're moving without friction, so we don't have to worry about that. This rod here has a resistance of 15 ohms. This rod has a resistance of 13.5 ohms. And here is 5 ohms of resistance. And the poles on the top and bottom, it says negligible resistance, so no resistance. And the problem asks us to find the current through resistor number 3. Ideas?
We solve for R1.
It tells us R1.
Yes.
Okay, I'm thinking we find the
No.
voltages.
We find the voltages.
Yes, okay. So let's start over here. We got a general equation. Epsilon is equal to B L V.
B is 0.0 T.
That is true. Epsilon, which is the voltage, is equal to the magnetic field times the length times the velocity. Okay?
Mm-hmm.
So you said what's B?
0.0 T.
So how long is the pole?
1.35 meters. Approximately 3.3645 inches.
Okay. And what's the velocity on pole number 1?
4 meters a second.
Okay. And now I'm just that good because I got it all in my brain.
Mm-hmm.
It's 0.0054 volts, right?
Mm-hmm.
So that's helpful. We'll box that. Now we just gotta do E sub 2. What's B?
0.01 Teslas.
What's the L?
The length of the second rod.
Yeah, it's the same L.
0.135 meters.
And what is the velocity of rod
2
number 2?
meters a second.
Okay, you're smart, right?
Sure.
If that's the same, that's the same. That's the same, that's the same. That's 4, that's 2.
Divide by 2.
So divide by 2. What's that divided by 2? What's 54 divided by 2?
26. Right?
Close.
27.
Okay, so what's this?
0.0027 V velocity.
Volts.
Volts.
I know it's confusing that they're the same V's,
Yeah.
but this is technically a big V and that's technically a little V.
Oh.
Alright, so now we got the voltages, so can we just do what we did with the last problem and just add them up? Why not?
They go in opposite directions.
True, yes and no. But before, it was one big loop in series because it was one wire. This time, since it's in the middle, it splits it up into 2. It's called in parallel. And you can't just do that the same. So what we're going to do over here is draw a circuit diagram. So we got a rod on the top. We'll just treat it as a line. And we said we got a resistor in the middle, right?
Mm-hmm.
Okay, well over here, since it has resistor, then we're going to put in what's called a battery, which is a voltage source, because remember it has that many volts. But we got to do a right hand rule to figure out which direction it's going to go. So the magnetic field is in the page, but it's increasing. Well, the area is increasing. So that means that the induced magnetic field the induced current is going to be this way, right? So that means that the positives are going to be down here, and the negatives are going to be up here. Okay? Do the same for this one. The magnetic flux is increasing this way, so the current's going to want to be this way. So we're going to have pluses up here and negatives down here, right? So it means since the positive's down here, we put the big one down here and the small ones. That's what it means. Big one's plus, little one's minus. So over here, we got more resistance. And then Which is the top one big or is the top one small?
Top one's big.
Top one's big. Little one. Okay. Now we're going to be using Kirchhoff's rules to write a systems of equations for this circuit. So what did we say this was? R1 13.5 ohms.
Mhm.
And this is 0.0054.
Mhm.
And this is 0.0027.
Yes.
This is 15 ohms. And this is 5 ohms. Okay?
Mhm.
I'll say I1 is right here, going this way. I2 is right here, going up. I3 going that way. And these directions, they're all just random. Okay, maybe I do know that those are the actual directions because I did the problem, but if you flip them around, you just get a negative sign, you just flip them. Not a big deal.
So it's positive, negative, like the.
Well, charge always goes from positive to negative. Like if this wasn't there, it would just go this way, positive to negative. Even though technically the negative charges are moving, because if protons move, you have a bomb.
I like bombs.
I know, but we're not here. So we'll start off with the easy one. If this is going in and that's going out and that's going out, what does this have to equal?
Positive.
So this is going in, right?
Mhm.
And those two are going out.
5.
So this equals
Those two.
those
Combined.
two.
You have to figure out those two though.
We'll get there.
Okay.
We're gonna do some tricks. So this is Kirchhoff's junction rule. Cause you know how like all energy has to be conserved? That's basically what this is. The stuff in must be the stuff out. Make sense?
Yeah.
Okay. And now we're gonna do what's called the loop rule. We gotta do some loops. So we're gonna start here. And we go down this way. So since it's current going through a resistor in this direction, it's negative. So it's negative I1 times 13.5 ohms. And then since we're going from negative to positive, it's plus. Make sense?
Mhm.
I'm going to go to the second line here. And again, there's minus because it's going through. Equals 0. This is also a conservation of energy thing. Because if it went in a loop and it wasn't 0, if it was like 1 and it kept going around, you'd have infinite energy, right?
It's good.
No. Well, it's good, but it's also impossible. So it has to equal 0. So we'll say that's number 1. That's number 2. And number 3. We're going to go, instead of going around this loop, we're going to go on a big loop.
Big loop.
Big loop. So it's going to start off the same. Okay, and now we're going to follow this one. So it's going from negative to positive, so we get a plus. And then the current's also going in this direction, so that'll be another minus. Okay, it's not bad. Let's clean it up a little bit. Number 2. I'll just rewrite number 2 because that's what equation it is, right? If you have a negative on one side, what happens when you bring it to the other side of the equation?
It's flipped. The thing it says positive.
Correct. So let's keep this on this side. That work for you?
Yeah.
I just put those on the other side. I'm gonna do the same thing down here. What's 0.0027 plus 0.0054?
82.
Close.
84.
Other way.
80.
What's 27 plus 54?
Oh. 81.
So this is?
0.0081.
I like it. Again, put that on the other side. I1 times 13.5 ohms plus I3 times 15 ohms. Okay, makes sense? Now I'm going to take this I1 is equal to that, and put it in. Because I'm not going to write it out because I'm running out of room. So you're taking this, you put this in there, right? And then you get an equation, then you get two equations with two variables, right? And if you were a senior at Marist High School, you would be able to solve an equation, two equations with two variables. It's called a system of equations. You guys get that?
It was really hard. I got a 46 on this. No, I got 56 on
Just
this.
two equations?
No, there was like 6. And the 6 was like 3 or 4. It was really hard.
4 variables?
Uh-huh.
Okay, so if they're doing it in, what grade are you in, 7th grade now? If they're doing it in 7th grade, seniors in AP Physics can handle 2 equations, 2 variables.
The best kid in the class got like a 73.
Okay, we'll have to do that later. Anyways, you put this all in, solve for I2. I2 is equal to 129 milliamps. An amp is a coulomb per second.
Aren't amps like sound? Like turn up to amp.
Yes. I don't know why it's the same name. Because it might be giving it more current. Probably is.
The more you know.
The more you know. Anyways, one amp is like a lot. Like, you know lightning?
Mhm.
That's like 3 coulombs. So like if you had 1 amp, that would be like a third of a lightning bolt every second.
That'd be awesome.
Yeah, except you'd like explode.
Yeah.
So milliamps means that's actually 0.000129 amps. And that's good. We like that because it won't blow us up. Okay. When I was first doing this problem, after I solved for the 2 different EMFs, I tried to first add them up, and that was wrong. And I tried to subtract them, and that was wrong. And then I was pretty mad that I couldn't figure it out. And then I realized that I had to draw a circuit and go back a unit and do Kirchhoff's rules.
Gesundheit.
Corona.
That's not a symptom. Seasick's not a symptom.
And then this shows my growth as a physics student because it shows that I'm able to apply EMF not only in stationary objects where the field's increasing, but also in moving objects where technically the area is increasing, but we could write it as the length times the velocity. Because, as you know, right Luke, as you know, V, what's velocity equal to?
The speed.
Okay, yes. It's the change in what over the change in what? What's speed mean?
Distance.
Over?
Time.
Nice. In calculus, when you'll get there in like 5 years, 6 years, it's dx over dt.
I seen that.
That just means, that means the same thing. It just means very, 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 very small changes. That's all it is. Very, 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 very small. Very small. Very, very small. And we know that EMF is equal to negative n d flux dt. Okay?
Mm-hmm.
What's flux? Flux is equal to the magnetic field times the area, technically. It's also
That's it.
the path integral of the magnetic field dot dA, but basically it's just that 90% of the time. And B's staying the same, right? B's not changing. It's just A's changing, right? So that means d flux dt is equal to B times dA dt, right?
Mm-hmm.
What's area equal to in a rectangle?
Length times width.
Yes. So this time we will do just LR. And length is constant, right? The bars stay in the same size.
Mm-hmm.
So dA dt is L dx dt. And we know dx dt is velocity, right?
Mm-hmm.
The n means number of loops. We got 1 loop, so that just canceled out, right?
Mm-hmm.
D flux dt. Well, flux is BA. D flux dt is B dot dA dt. And dA dt is LV. So that's where this equation came from. Someone did this in physics, and it was important.
Kershich. I have 2 questions.
Oh, you got questions? Okay.
So on the top of the rods, you
Yes.
have like negative and positive charges.
Yes.
Is there a reason there's only 3 positive?
No. There's actually millions and billions of them, but I didn't want to draw them all.
Okay, and you put the backwards E. You said like EMF. Why is it just an E?
That's just the symbol we use. There's no really good reason for it. You know what I mean? Here is the entire problem. I did not realize I was missing the top portion of the problem until after I have already done it and I was not about to do it again. Thank you.